Dear students, welcome to another day's lecture in Elements of Machine Design. We were seeing about the couplings. See, here is a picture of an electric motor and a pump, which is used for a centrifugal pump, which is used for pumping water. Okay, you see, this is the shaft of the motor, and this is the shaft of the pump. You see, is it necessary that both should be of same size? Not necessary. And here the thing that is joining in between these two, that is the coupling. We have seen the flanged coupling. This is a simple flanged coupling, or it is also called as unprotected flanged coupling. See, the diagram is like this. So we will see the design of these things. What are the important things? This is the shaft. The keys are at an right angles. If you see in the side view, this will be at right angles, and the diameters, this capital D, D1, D2, these are the important things. The diameter of the bolt and the thickness of the flanges, TF. Okay, and this is the thickness, the length of the flange. These are things that are important. Okay, similarly, uh, when you come to the protected type, this is the protected type flange coupling. Only that there is a little protection that is provided. Protection means to protection to whom? I see, when it is rotating, it should not catch any of the loose garments or something, or any sleeves of the shirts, and it should not pull, or it should not hit the hands of the workers. So some protection. So when it is like this, the nuts and bolts are not exposed. That is why protection. You see, this is much similar, only that there is this TP extra. This is the thickness of the protection. TF is the thickness of the flange, TP is the thickness of protection. Only that this, and the proportion also is given 0.25 D, and that's what you have to use. Okay. Then next, there is another coupling called as marine type flange coupling. This is also much similar, only that you know, this shaft itself. It's, you see, there is no key involved. Shaft end itself is forged in such a way that this becomes a flange. And also here we are not using ordinary nut and bolt. This is some tapered bolt is used, and nut. Okay, this is called marine type of flange couplings. Marine means, this must be, they must be using these things for use in ships and other things, in the sea applications. Marine application means sea applications. Okay, then okay, 1 minute. Yeah, this is another coupling. This is called a bushed pin flexible, again flanged coupling. And here, there is a little difference. What is the difference? Here, instead of the nut bolts, we are using something called as pin. Okay, this is the pin, and about this pin there are bushes provided. One brass bush and one rubber bush. These two bushes are provided. You see, this comes under the category of flexible coupling. The name itself is flexible is there. A little bit of flexibility. How much of flexibility? In what way it is flexibility? If any angular misalignment is there, and that misalignment may be, it varies from, it may be some 2 degrees, 3 degrees, maybe maximum 5 degree, not more than that, of angular misalignment is there. This can be taken. This also will design. You see here, you see there is a space, 5 mm space between these two. Are you seeing it? Okay, so this is the change when we are designing. Is we will see how it differs. Okay, we have already seen this is how the rigid flanged couplings are seen. They are widespread in use. They are simple in to they're simple in construction, and they are rigid couplings. They transmit force by shape and friction. That's it. There is another rigid coupling here. Can you identify this coupling what it is? This coupling is simple muff coupling or sleeve coupling. Okay. And without the split, you see the advantage of this, there are no projecting parts. So there are no projecting parts, therefore no, less chance of accidents and other things. But the thing is, more space is required to insert this sleeve in the middle. Okay, and this is the universal coupling. Universal coupling here, you know yeah, universal coupling assembled, you can see here is the double universal joint. This is a single universal joint. Here double universal, if it is a resistance also, you know you can do it. This is the universal joint. This is also called as Hooke's joint or Hooke's coupling. And here is the comparison between rigid coupling and flexible coupling. See, what is the purpose? This is used for connecting perfectly aligned shafts, and this is used for small misalignment if it's present. Alignment, see, it cannot tolerate any misalignment. This can tolerate misalignment. Shock and vibration, this cannot absorb any shock or vibration. This can absorb shock and vibration. Not everything, some of the things. Deflection is less, deflection is more. Cost is less expensive and more expensive. Now let us come to the design of the unprotected flange coupling. We have already seen the design of muff coupling. Now let us see about the flanged coupling. You see here, let D be the diameter of the shaft, and for our design now we are assuming both shafts are of same diameter. Okay, but in actual practice there may be differing. Okay, then the outside diameter of the hub, this is capital D, which is taken 2 times of the diameter of the shaft. These are empirical relations. You see, you get all the dimensions here itself just by looking at the figure. Okay, D1 is the PCD means pitch circle diameter of the bolts. That means from the center point of the bolt here to the center point of the bolt here. uh, you know that is the PCD. PCD is 3 times of the diameter, and then the outside diameter is outside diameter of the flange is taken as 4 times of diameter. You see, this is 1 time diameter, this 2 times diameter, this 3 time diameter, 4 time diameter. Is very simple to remember, is it not? And then see, this little projection is there, that is 1.5 times of the diameter. And the length of this is the flange. The length of the flange is 1.5 times of the diameter, and this diameter is D1. You see, this is D1. Okay. And then TF also is the length of the flange, and that for that also some proportion we will use. So these are the notations we'll be using: small d, capital D, small d1, capital D1. N is the number of the bolts, TF is the thickness of the flange, and tau S is for shear stress for shaft, tau B is the shear stress for bolt, tau K is the shear stress for key. All may be different materials. Okay, but it can be same, for us when we are solving problems. It will be simple. Tau C is the allowable shear stress for flange material if it is cast iron or something. Okay, flange. Yeah, see, shaft, bolt, key, flange. So many things are there. Okay, sigma CB, sigma CK. These are the crushing stresses for bolts and keys materials respectively. Now the first step, whether it is a shaft or whether it is a key or whether it is coupling, first step is to design the shaft. So for designing the shaft, what we do is T is equal to pi by 16 tau D cube. From that we first find the diameter D, and afterwards the second step is design of the hub. In this design of the hub, we will design it considering to be a hollow. But all those things, are already according to the proportions we have found out. What are we doing then? We are only finding out the what is the induced crushing stress, or whether this is within the permissible limit or not. So with this formula, T is equal to pi by 16 tau d to the power 4 into 1 minus k to the power 4. So this is the formula that you should use for designing the hub, considering it to be a hollow shaft. Okay, the outer diameter of the hub is usually taken as twice the diameter. Therefore, from the above relation, the induced shear stress in the hub is checked, and the length of the hub is taken as 1.5d. See, this is also proportion. In the figure itself, we have seen all the proportions. Next is the design of the key. The key is designed with usual proportions, then checked for shearing and crushing stresses. Okay, usual proportions means d by 4 and d by 6, that is the width and the thickness. And the material of the key is usually same as that of the shaft, and the length of the key is taken equal to the length of the hub. Length is according to the whatever is the length that we should take. And the design of the flange, uh, the flange at the junction of the hub. You see, the junction of the hub is under shear. You see, when this is rotating and the key is rotating, this is rotating, and these nut bolts alone are stationary. Suppose this is rotating, this is not rotating. What will happen? It will shear here. You see, it will cut here. How it will cut? It will cut on the circumference, entire circumference. You see, 1 minute. You see, like this thing is there, no? If this part is rotating and this is not rotating, this flange is not rotating, this hub is rotating, what will happen? In the joint here, the entire circumference, it will shear off. That is the meaning. Okay, in that case, what will be the this thing area of failure will be the circumference is pi capital D, and the thickness is TF. Pi D TF, that will be the area. Okay, so that you should put here. Okay, circumference of the hub and thickness, this is the area, into shear stress into radius will give you the torque. Okay, so mathematically it will be T is equal to pi D into TF tau C into D by 2. Okay, from this, the thickness of the flange is usually taken as half of the diameter of the shaft. Thickness of the flange, that means TF is 0.5 small d. Therefore, from the above relation, the induced shear stress in the flange can be checked. Then next come the design of bolts. See, bolts, how do they fail? Bolt, if we see here, this bolt, suppose, now uh, when we are designing this, we thought that this is not rotating, other things are all fine, so here it sheared. Suppose now when we are designing this, what we'll think, this also is trying to rotate, only that this is not rotating. That then what happens in the middle? This this bolt get sheared off. How many nuts at the same time? Suppose there are 8 nuts there, so 8 nuts should be sheared. If there are 4 should be sheared, like that. Okay, so the bolts are subjected to shear stress due to the torque transmitted. Okay, see, the number of bolts is small n. Okay, this depends upon the diameter of the shaft. The pitch circle diameter, capital D1, is taken as 3d. This we saw in the figure itself. Load on each bolt is, what is the area of the bolt that is resisting? Pi by 4 d1 square. And if you multiply this by shear stress, you will get the load on one bolt, and there are n bolts, so total load is this into small n. Therefore, the torque is transmitted to capital T is equal to pi by 4 d1 square into TB into n into d1 by 2. Why d1 by 2? Where are the bolts? Bolts are at a distance d1. This is d1 by 2, because from the center you have to take the distance. You see, when you are designing the key, the distance is only small d by 2. When you are designing the hub, it is breaking here, this distance is capital D by 2. When you are designing bolt, it is this distance, so that this distance is capital D1 by 2. You see, like that, these things are changing in at every point, for key, for flange, and for bolts. Okay, from this equation, the diameter of the bolt may be determined. You can calculate it. Now the diameter of the bolt, then you should check for crushing. See, two things in which this may fail. One is in shearing, the other is in crushing. Crushing, the area will be this much area. Okay, that means the projected area, this TF into D it should be. Okay, TF into D and n number of bolts. So this is the crushing area. You see, you should be think a little about how this area comes. Crushing area is the projected area. Okay, how the crushing takes place, you see, and you should consider only in half of the in this flange alone, not the entire thing, because crushing takes place in the half flange only. Okay, so the total crushing strength, you will get this equation. From this equation, induced crushing stress can be checked, and if it is within the limit, it is safe. See, that's all. That is the design of the flanged coupling. See, one is design of the shaft first, then you can design the key also, and design the flange, and design the nuts, design the bolts. Okay, and afterwards the other things, outside diameter and other things, these are proportions, this length and this TF are all proportions you can take. Okay, so accordingly we do the design. Next is bush pin flexible coupling. Let us see the design of this. The bush pin type of flexible coupling is the little modification from the rigid flange coupling. The coupling bolts here are replaced by these pins. These are called pins. This head is not hexagon, it is cheese headed bolt. It looks circular. Okay, a clearance of 5 mm is left. 5 mm of clearance is left between the face of the two halves of the coupling. This is one half of the coupling, this is another half. Between them 5 mm is left. Okay, next, this bush pin type flexible coupling, the main modification is to reduce the bearing pressure on the rubber or leather bushes, and it should not exceed 0.5 mm 0.5 Newton per millimeter square. Okay, you see here, no, instead of the nut bolts, simple bolts, we are using pins. Okay, this pin we are using, this is called a pin, otherwise you can call it as cheese head bolt or something. Okay, and here the bearing pressure should be within 0.5 Newton per mm square. Okay, within that you should maintain. See, actually, because there is a rubber bush here and also brass bush here, so it is allows a little angular misalignment, so maybe 2 to 5 degrees. Okay, in order to keep the low bearing pressure, the pitch circle diameter and pin size are increased. Pitch circle diameter also and the pin size also, they are increased, it seems, because this should be less. Okay, now let L be the length of the bush in the flange. See, L is from here to here. You see, this in this gap also, in the gap of 5 mm also, the bush is there. Okay, D2 is the diameter of the bush. D2 is the diameter of the bush. Actually, here head diameter they are showing. Actually, that is not the D2. D2 will be from here to here. Okay, like that. And BB is the bearing pressure of the on the bush. Now, N is the number of the pins. How many pins we are using? And capital D1 is the diameter of the pitch circle. This one, this is the capital D1. Okay, and the bearing load acting on each pin. See, all the pins are like this only. Okay, so the bearing pressure that is acting on these things is, see, bearing pressure has crushing stress, bearing stress, pressure, bearings pressure also. For that, we what we consider is the projected area. Projected area. This is this D2, and this distance is L. L is they have taken here. Okay, within this only, in this gap there won't be bearing. So after the gap only, from the gap to this side, that only will be the bearing area. This is the projected area, D2 into L. And if you multiply that with the bearing pressure, you will get the bearing load. Okay, on each pin. Like that, how many pins are there? There are n number of pins. So the total bearing load will be given by PB into D2 into L into N. Okay, then the torque, that should be equated to torque. This is the load. And okay, whatever is we are getting here, that multiplied by the radial distance from that place to the area of failure, that means this capital D1 by 2, if you multiply, you will get the torque. This is, see, W into N is the load and D1 by 2 is the distance. Okay, like that. You see, if you see this pin, a head should be here, head is not shown, and this is the pin, and at the end of the pin there is a threaded portion. Okay, and this thread, on the threaded portion, this nut is fitted, and the threaded length of the pin should be as small as possible so that direct shear stress can be taken by the unthreaded neck. You see, the direct shear will be taken by the unthreaded neck. Okay, the direct shear stress due to pure torsion in coupling halves will be. See, apart from the bearing pressure, one more thing. Why did we consider crushing in case of flanged coupling, and in case of bush pin type we considered bearing pressure? There we consider crushing because there is no we are almost no relative motion, because nuts will not be rotating there. But here, no, because of the misalignment, there may be relative motion between these two. That's why we are considering bearing pressure. Okay, this is a little difference compared to the flanged coupling. Okay, and also, see here, two types of failures in this. One is direct shear. It may shear off like this here, and the other is bearing pressure. First we have seen the bearing pressure. Now we are considering shear. Shearing means if it is cutting like this, if it is cutting like this, then you know it is it is cutting means, see, this diameter is d1, so the area that is cutting is pi by 4 d1 square. Okay, this is for each bolt or each pin, you can say. Since the pin and the rubber or leather bush is not rigidly held in the left hand flange, therefore the tangential load W at the enlarged portion will exert a bending action on the pin as shown in figure. You see, this is the, see, now these are not rigidly held, you see, because the bushes are there. Okay, then what, this load is coming, this entire thing load is coming, this W. Suppose the where you can say it is acting, resultant is acting at the center, you can say. So it is as good as some bending is coming, only one W is acting here, and it is like a cantilever or something, because of which you have to consider bending failure also. Now the third thing we are considering, one is bearing pressure, the other is direct shear, and the third is bearing bending. So the bush portion of the pin acts as a cantilever of beam L, not only L, plus 5 mm also. Okay, see, if you see here, this W is acting at the center, is take, And center means what? It is at the distance of L by 2, and also there is a gap of 5. So this L by 2 by 5 will be the distance at which this is acting. Okay, and that into W, this will give you the moment. And once you know moment upon section modulus, this is for each pin we are calculating. Okay, for the section modulus is the bending stress is bending moment upon section modulus. Bending moment we are getting W into L by 2 plus 5 divided by Z is pi by 32 d1 cube. Okay, since the pin is subjected to bending and shear, you see now, see, crushing is different. Bearing pressure is different. That is a localized stress. But these are bodily stresses. These body stresses are two. One is bending as well as shear. Two are there. Okay. See, this is bending stress is sigma, sigma stress. Shear stress is tau stress. These are two different, categories of stresses. Therefore, the design must be checked either for maximum principal stress or maximum shear stress by the following relations. Now, what do you have to do? You have to go for principal stresses, because there is sigma also, there is tau also, and you know that maximum principal stress formula is half of bracket sigma plus square root of sigma square plus 4 tau square. Okay, this is the maximum principal stress. And if it is a maximum shear stress, then it will be this one, half of square root of sigma square plus 4 tau square. So these are the two formula by which you can find out the principal stresses. This is maximum principal stress, that is sigma 1. This is the maximum shear stress, that is tau maximum. Okay, and the value of principal stresses varies from 28 to 42 MPa, depending upon this material. This value depends upon the material. Okay, after designing the pins, the rubber bush, the hub, key and flange may be designed in similar way. I think we can see one problem. Yeah, you see this problem. Design a bushed pin type flexible coupling to connect a pump shaft to a motor shaft transmitting 32 kilowatts at 960 RPM. The overall torque is 20% more. You see, this is 20% more torque. That means what? If you are considering T maximum will be 1.2 times of T mean. Okay, than the mean torque. The material properties are, the allowable shear stress, this means and crushing stress for shaft and key. This is for shaft, that means tau for shaft and key. They said, okay, that is the same material. That means this tau k or tau s is 40 MPa, and this is crushing stress will be 80 MPa. Okay, for shaft as well as key. Okay, and then allowable shear stress for cast iron is 15 MPa, that is tau c is 15 MPa. See, this will be much less compared to this. Okay, this is because mild steel and this is cast iron. Okay, and the bearing pressure is only 0.8 Newton per mm square. Okay, and then first what you have to do, okay, find the diameter of the shaft. Okay, for diameter of the shaft, first you have to find out what is T. If T is not directly given in the problem, power is given, therefore we have to calculate T. So first T is T, what we are getting here in this power equation is mean torque. So we are getting mean torque this much, 318.3 Newton meter, and then the maximum torque you have to calculate, because they said 20% more, so you have to multiply it by 1.2. Okay, and then what you have to do is the torque transmitted by the shaft is this much, capital T maximum is 7.86 d cube. In terms of d cube you are getting, and that you equate to shear stress of the shaft. Okay, and when you equate that, you will get this value 36.5, and they have rounded it to 40 mm. Okay, Now next, what you have to do next is, we have discussed in rigid type flanged coupling that the number of bolts for 40 mm diameter shaft are 3. Actually, you will get a table there. If it is 40, it is 3. And when you should take 4, when you should take 6, like that. In flexible coupling, we shall use the number of pins n as 6. Okay. You see, okay, for our thing here, we take it 6. Actually, in real practice, it depends upon the diameter of the shaft. Okay, so the diameter of the pin D1 will be 0.5d upon square root of n. This is the formula that we are using. Okay, this small d is the diameter of the shaft. Okay, this comes to 8.2 millimeters. Okay, the length of the pin of the diameter is the length of the pin of least diameter, that is capital D1, is 20 mm, is threaded and secured in the right hand coupling half by standard nut and washer. You see, actually, no, what I see is that there are threads in the right hand coupling half also, and also nut washer also are there. Okay, and the length of the this is the length of the pin of least half of the diameter of D. That is the thing. So here they say length of the pin of least length of the pin L1, it should be, is it not? 1 minute. Okay, this must be the diameter only 8.2 is actually what we are getting, but minimum that you should take is 20. So they are taking 20. Okay, the enlarged portion in the left hand coupling is made of 24 mm diameter, a little more than that. The enlarged portion, on the enlarged portion, a brass bush of 2 mm thickness is pressed. A brass bush carries a rubber bush, and the rubber bush thickness is 6 mm. This is 2 mm and 6 mm thickness. Okay, that means on the radius side 2 mm is increasing, on the radius side 6 mm is increasing, 8 mm is increasing on this. Okay, in that you will see. So therefore, the overall diameter of the rubber bush will be D2 is equal to 24 plus 2 plus 2 plus 2 into 2 plus 2 into 6. So 40 mm. Okay, so the diameter of the pitch circle diameter will be, you see, then you can calculate 2D plus D2 plus 2 into 6. That is, see, 2 times of the diameter plus 40 plus 12. From where are you getting this? See, from where are you getting this? See, this is the hub diameter, capital D, and this gap, no, this is taken as 12 mm. This is taken as 12 mm, like that. That's how from there you are getting. Okay, and then see then the length of the bush in the flange is L, and the bearing load acting is D2 into L into PB. Okay, PB is given. So this is 40. We have calculated into L. Okay, that means W is 30 into L. Okay, and this multiplied by D1 by 2 will give you the torque. So torque is equal to, that is maximum torque only. On all designs, no, you take maximum torque. Okay. So 32 into L into 6 into 132 by 2, you will get this value, and tau maximum, therefore from that you will get L, and L will be 30.1, say 32, and and you can find out what is the W in that case will be 32 into L, and this comes to 1024 newtons. And then the direct stress due to pure torsion in the coupling halves. In the coupling halves, direct stress will be, see, uh, where it will be failing. It will be failing at the you know at the what is failing? Direct stress due to poor torsion in the coupling halves. In the coupling is failing at D1. Oh, no. This is not coupling. This is the direct shear stress in the pin. That's why we are using D1. So this is pi by 4 into 20 square. You see, in the not in the enlarged, the shearing will not take place in the enlarged portion. Shearing will take place at the minimum section, where minimum section is a small d1. Okay. So the pin and the rubber bush are not rigidly held, therefore you have to consider it as a cantilever, and then from there you have to find out. Earlier we have seen how to calculate the bending moment and the section modulus you calculate, and then from that you calculate the bending stress is it comes to 27.4 newton meter. Then you calculate the principal shear stress, maximum principal shear stress, and maximum shear stress. These two formulae we have already seen. Okay, you are getting this much for the 27.8 and 14.1. Since the maximum principal stress and maximum shear stress are within limits, you compare with the permissible stresses, then the design is safe, we can conclude. Okay. And now design of the hub. Design of the hub, you see, this also you can do first than that one, but in this book it is given like this. So we have designed the pins first. Okay, now capital D is 2 times of diameter of the shaft. So this is 80 mm. This is by the empirical relation. This is also length of the hub also is by empirical relation 1.5 D. Okay, it is coming to 6. And then here you can calculate the induced see, considering as the hollow shaft, you can see, and you can find out what is the induced shear stress, and see if this is within the permissible limits. Okay, and then next, design of the key. Design of the key you can take from the data books. Otherwise, what you can do is width will be d by 4, and and thickness is d by 6. With that you can calculate, and then you can check the induced stresses. Induced stresses, one in shearing and one in crushing, within the permissible limit or not, you can check. Okay, and that is what they have checked here in this thing. I am going further. Then the design of the flange. Design of the flange. The thickness of the flange is taken as 0.5D. This is an empirical relation. Okay, and how the flange fails. Flange fails at the at that place. You see, flange fails at the junction of the hub. Okay, so this is the formula that we have already seen. Pi by say pi d square by 2. You check this formula whether this formula was the same as before, and from this what you can do is you can find out the crushing induced shear stress, and see how much it is being induced. It is being induced is 1.9 MPa only, whereas 15 is the permissible thing, so it is safe. Okay, so with that that's all. You see, what are the things that we are designing? When we are designing, you see, what all we have to design? We have to design the shaft, we have to design the hub, and we have to design the flange, and then we have to design the pins. Okay, so if you if you open your book, you follow the procedure that is given, that is followed by those people. If any problem, you contact me. So with this we finish this chapter. Now this third unit is finished. Okay, and in the next lecture we'll start a new unit, a new chapter. Okay, thank you very much.